In our last lecture, we introduced the Fourier series for a periodic function f r to r. Under some condition, we can have the Fourier series of f here. A, k, b, k are the Fourier coefficients given by integration. A k is 1 over pi fx cosine kx dx. Bk is 1 over pi fx sine kx dx. Okay, so a basic question is whether this series converge. This series converge, and if it converge, what's the sum of the series? Is it fx? To solve this problem, we prove the Riemann lemma. If f is integrable, absolutely integrable in the interval a, b, then fx cosine px dx goes to 0 as p goes to infinity. Of course, this is also true for sine px. Okay, this is what we talked about last time. Now we will solve the convergence problem today. So for this purpose, we need to compute the partial sum of the Fourier series. So in the computation of the partial sum, we need some formula. The first formula, alpha plus beta, is cosine alpha cosine beta minus sine alpha sine beta. And the second formula we need is cosine alpha sine beta half of sine alpha plus beta minus sine alpha minus beta. Okay, we will use these two formula. Now, to study the convergence problem of this series, we study its partial sum. Okay, so we assume that f is absolutely integrable. That is minus pi is finite. Okay, so the partial sum of the Fourier series is given by denoted by S and X. S and X is the first n term of the series ak cosine kx plus bk sine kx. Then substituting the expression of ak and bk into this series, we obtain that this is 1 over pi minus pi a half plus ak is cosine kt fx, we write fx at the very end, so cosine kt cosine kx plus sine kt sine kx, then ft dt. We change the integration variable in the expression of ak and bk by t, because we already have x here. So the coefficient, the expression for the coefficient of ak and bk need to replace by another letter, say t. So the integral of cosine kt ft is ak. Okay, Similarly, sine kt ft is give us bk. So we need to simplify this expression. Now using this formula, this result can be written by one over pi minus pi a half plus the sum of cosine k t minus x ft dt. Okay, just use the formula 1 in this part. Every term here, you will obtain the cosine kt minus x. Then go to next page. We need to compute the sum of cosine k theta, k from 1 to n. Okay, we computed this separately. Compute this part separately. Okay. So a half plus sigma k from 1 cosine k theta, we denote the t minus x by theta. Then this can be computed in this way. Half of this plus 2 sine half of theta, then k equal to 1 cosine k theta sine half of theta. Okay, then maybe I will write this more clearly. 2 cosine k theta sine half of theta. Then we apply the second formula. Cosine alpha sine beta equal half of sine alpha plus beta minus sine alpha minus beta. So using this formula, our computation goes follow. This is a half plus 1 over 2 sine half of theta. Then when k equal to 1, what's this? When k equal to 1, this is sine 1 plus a half theta minus sine 1 minus a half, that is a half theta. This is for k equal to 1. So for k equal to 2, that is sine 2 plus half of theta minus sine 2 minus a half, that is this. Then plus the last term is sine n plus a half theta minus sine n minus a half theta. Okay. Then this sine cancel with this term, and this term will also cancel with the next term. Finally, this term will also cancel with the previous term. So what remains are these two terms, this term and this term. Okay, then we obtain a half plus 1 over 2 sine half of theta sine n plus a half of theta minus sine half of theta. Then this term cancel with the denominator, you obtain the minus a half, then cancel with the first minus a half. So the final result is 2 sine half of theta sine n plus half theta. Okay, we have this high school computation. So apply this high school computation into our previous computation of the partial sum of the Fourier series for this part. For this part, we can use the computation we just developed. So we can continue this computation. Continue our computation to obtain that the result is 1 over pi minus pi pi sine n plus a half. Then our theta is t minus x over t sine half of t minus x, then ft dt. And this can be simplified further. We make a change of variable. Let u equal t minus x. So this can be simplified by change of variable in the integral minus pi minus x pi minus x sine n plus half of u to sine half of u. Then f t is x plus u du. And since f is periodic, sine is also periodic. Okay, so this integrand in this integral is periodic. So for a periodic function, the integral over any interval of the same length of the periodic are equal. Therefore, this interval, the length of this interval is 2 pi. 2 pi is the periodic of the integrand function. So we can switch this interval of integration by another interval of length 2 pi. So we write this by minus pi sine n plus half of u to sine, then fx plus u du. Okay, this step is very crucial because it simplified the upper limit and the lower limit of the integral. We can do this because the integrand is periodic of 2 pi periodic. So we can do this. Otherwise, we could not. Okay. So having obtained this result, because this is an even function, replacing u by minus u, this fraction remains unchanged. Therefore, we can divide the interval of integral by 0 to pi and minus pi to 0. And then in the minus pi to 0 interval, we make a change of variable u by minus v. So a simple computation will obtain the 1 over pi minus pi, sorry, not minus pi, 0 to pi now, 0 pi sine n plus half of u to sine u over 2, then fx plus u plus fx minus u du. The x minus u term comes from the integral over minus pi to 0, which is a change of variable. Okay. So this is the integral representation of the partial sum. Okay. Now, as a particular form, we take f to be identically 1. F identically 1. Then what we get? Then our A0 is 2 over pi minus pi f. That is 2. A0 is 2. And the other AK are 0. AK equal BK equal 0. Okay, by the also because 1, the function 1 is orthogonal to cosine kx and sine kx. And the ak and the bk are obtained by fx cosine kx integral, because now f is 1, perpendicular to cosine kx and kx, so the integral, that is the inner product, must be 0. So the other ak and the bk are 0. So a0 is 2. So our this formula Sn, our Sn in this Fourier series, Sn just 2 over a0. The other ak bk are 0 for f equal to 1. Okay, so the left hand side is a0 over 2, that is 1. So we obtained that that 1 equal 1 over pi 0 pi sine n plus a half of u sine a half of u du. Maybe I keep the 2 here. So in this case, f equal to 1, fx plus u plus xx minus u are 2. So we have a 2 here. Okay. So this is a very useful result. So in conclusion, we have Snx equal pi 0 to pi sine n plus a half of u 2 sine a half of u fx plus u plus fx minus u du. This is what we have computed. And the other useful result is the particular case we take f identically 1. Then this blue formula at the right lower corner. Okay, so we copy it here. 1 equal 1 over pi 0 to pi sine n plus a half of u 2 sine then 2 du. Okay, so we have these two useful